Alright, once you know whether or not a reaction is first order, second order, zeroth order, third order, etc., we can use the rate law to calculate rates given various concentrations, but there's a much more useful form of the rate expression called an integrated rate law, and it's called the integrated rate law because we use calculus on the rate equation, on the rate law, to get this more usable form. Now it requires that you be talking about specifically a reaction that is first order, for example. And so what we're going to do is we're going to go through the integrated rate laws for zeroth order, first order, and second order. If you go on and take physical chemistry, you will get into more detail about this, but at this point we essentially have to learn these equations. If you are talking about a first order reaction, you know that it is first order. Recall that the rate law looks like this. We have the rate is equal to K, the rate constant, times A, the reactant raised to the first power. And recall from early on in the chapter, this was also equal to the negative change in concentration of A with respect to the change in time. A little bit of calculus allows us to rearrange this equation in a very usable fashion, and we get what's known as the integrated rate law for a first order reaction, and it looks like this. Alright, a little bit of an explanation is involved here. If I have the concentration at time t with a sub t, that's literally what that means. That's the concentration after a certain time. The brackets around A with the little naught subscript mean the initial concentration. K is my rate constant as above, and t is the time period that you're talking about. So this equation, which has a couple of different forms, but this is one of those forms. This equation essentially has four variables. It has the concentration of our reactant after a certain time, an initial concentration of our reactant, a rate constant, and the time period we're talking about. And typically we use this in the cases where we know three of these variables and we're trying to find a fourth. Now that requires that you be able to handle mathematics involving logarithms. This might be a great time to review logarithms, but here we have this formula, which is our first order integrated rate expression. A little bit of algebra leads me to a slightly different way to write this. This is the equation for a straight line. Recall that a straight line is y equals mx plus b, so if I know that I have a first order process, a plot of the natural log of the concentration versus the time, so the log of the concentration on the y-axis, the time on the x-axis, gives us a negatively sloping straight line, and the slope of that line is negative k, the negative of the rate constant, and the y-intercept is the natural log of the initial concentration. So these are two very useful formulas or formats for a first order integrated rate expression and the graphical analysis. Now let's talk about a second order. If I have a second order reaction, we're going to simplify it talking about only one reactant at a time. A second order process has a rate law that looks like this, where we have rate is equal to K times the concentration of A, whatever my reactant is, raised to the second power. And again, this is the negative change in the concentration of A versus time. Again, a little bit of calculus, which we won't go through, leads us to the integrated second order rate law that looks like this. Again, as we saw before, we have an equation with four variables: the concentration at time t, the initial concentration, the rate constant, and the time period you're talking about. And typically you're going to use this equation if you know that it's second order. You have to be talking about a second order reaction for this equation to work, and you're given three of these variables and you're trying to find a fourth. A little bit of algebra leads us to another useful form for this reaction. And again, this is the equation for a straight line, y equals mx plus b, and so a plot of 1 over concentration on the y-axis and time on the x-axis gives me a straight line. In this case it's a positively sloping line where the slope is equal to the rate constant k and the y-intercept is equal to 1 over the initial concentration. Again, two useful forms of my integrated second order rate law. Let's talk about a zeroth order. A zeroth order reaction, these do happen. We're looking at a rate law that looks like this. Essentially, rate is equal to k times a raised to the zeroth power. Recall that a to the zeroth power is a 1. You end up with a very simple expression for the integrated, again, doing a little bit of calculus. The integrated rate law looks like this. As with the other integrated expressions, you have 4 variables. And typically you use this equation when you know that it's zeroth order and you're given 3 of the variables and you're trying to find the 4th. A little bit of algebra, we can rearrange this, which is the equation for a straight line, y equals mx plus b. And in this case, we have concentration on the y-axis, time on the x-axis. This gives us a negatively sloping line with a slope of negative k. And a y-intercept is my initial concentration. And you may recall this from the first video on kinetics, the very first day that we talk about it. We talk about looking at the concentration versus time, and typically we get a curved line, except for in the case if it's a zeroth order reaction, then we do see a straight line for that. We do see just a drop off of the concentration versus time.